Good afternoon. I'd like to welcome you to the first of our Bowie lecture series. And today we are going to honor Dr. Joe Huba with the Marcel Nicolet Lecture for Aeronomy. And in recognition of the importance of this award, we have somebody to introduce him, a longtime associate, Professor Dennis Papadopoulos. Dennis, would you say a few words?
Well, let me start by first congratulating Larry and the selection committee for the outstanding selection of Joe Huba for the Marcel Nicolet Lecture today. I also want to thank him for providing me with the pleasure of saying a few words for Joe. I met Joe more than 40 or 45 years ago, I don't remember years anymore, when he was a graduate student of Shinru at the University of Maryland. He soon thereafter became my NRC postdoctoral fellow at Naval Research Laboratory, and it was a pleasure to work with him. At that point, Joe had an outstanding training from Shin on linear plasma physics. My role was to get him to the nonlinear plasma physics, anomalous transport, the controversies of the society, and that continued till today. I still work periodically with Joe, and last year he was a co-advisor of my latest graduate student, Katie Zodi, who is sitting somewhere there. At this point, I do want to pay homage to the person I consider Joe's major mentor, and that was Sid Osako. He was the one that introduced him to ionospheric plasma, irregularities, striations, communications, all aspects of that. I'm sure Sid is looking down to us, being very, very happy. Another person with major influence on Joe was Glenn Joyce, who introduced him to the intricacies of computational physics. Joe has been a wonderful scientist, a wonderful mentor, and had major influence in ionospheric physics, especially with the series of SAMI codes about which you're going to hear next. Congratulations, Joe, for an excellent career, and I wish you the best for the future.
Thank you, Dennis. And now let's welcome Dr. Huba, please.
Okay, thank you. Thank Larry and the committee for selecting me for this honor. I'm really proud of it. And for Dennis's comments, I remember my first day at NRL. It was October '75. I showed up at Building A50, found Dennis's area, and his secretary, Judy, looked up and said, "You're the new postdoc. Dennis is on travel, and we don't have any room for you." At which point we walked down the hall and she said, "Oh, this is Asakow's office. He's not here. Sit here." So apparently on day one I was preordained to go into ionospheric physics, so I didn't know it at the time. Okay, so to open, I'll just simply say that I think over the years I've been something of the front man for SAMI3 and giving the talks and writing lots of papers. But I think my colleague Glenn Joyce, who unfortunately passed away about 6 years ago, played a primary role. And so I'll mention his name a few times during the talk, and it's just nice that there be a face to his name because he was a really, really great guy. All right, so the beginning, it's sort of the story of how we developed the code and where we went with it. So I think it was spring of '97 when I went in Glenn's office and said, "Let's build an ionosphere model," and he said, "Okay." At the time, I was literally thinking, I don't have a clue as to how to build a model of the ionosphere, but Glenn's a great computational physicist, he can do it. And I don't know what Glenn was thinking, but I teased him later on that he was probably thinking, I don't even know what an ionosphere is, but Joe does, he can build the model. So I think armed with a lot of confidence in the other guy, we went forward. But we actually had some help. Literally, NRL had developed an ionosphere model in the early 70s, the original SAMI, and the S is for simple, and it was very simple. It was a 1D model of a mid-latitude ionosphere with a straight magnetic field line. We had the code, we had the paper. It was quite well written as far as the code's concerned, and it laid out a blueprint for how to build a model. But again, we wanted to do a lot more than this. So the second bit of help we had was from the STEP Red Handbook, edited by Bob Shunk of Ionosphere Models. And in that book, there were some papers by Graham Bailey, who authored the SUPIM code, Sheffield University Plasma Ionosphere Model. And in his papers, he really went into the nitty-gritty of the equations, what was going on, how he was solving them. So this was like a super big aid in terms of how to build a model in the context of the original SAMI. So we went forward. These are the equations we're solving: continuity, velocity, temperature, electron momentum, temperature, and electrostatic potential. So I've shown my equations. Will not go into any detail, but the point is they're relatively complicated, and how are we going to solve them? And so the two numerical issues are transport and the gridding. And under the transport issue, we have the advantage in the ionosphere that it's a low beta plasma and it's highly magnetized. So parallel motion and perpendicular motion can be decoupled. And so numerically, we can solve along the magnetic field line, including photoelectron or photoionization and chemistry and the like. And then the next iteration, we can do the E cross B transport across the magnetic field. So that's the idea. So for parallel transport, we chose the conventional technique that everyone had used. No details, but the idea is you ignore electron or ion inertia. You solve this equation for VIS, the velocity. You substitute it into the continuity equation. You can do a lot of algebra and come up with an implicit scheme to update the density. Okay, so this is what we did. An advantage is that it takes large time steps, 5 to 15 minutes. There's no Courant condition to really worry about. The disadvantage is it's kind of complex. It's easy to say solve for VIS and substitute in here, but you have a multi-ion species and all the ions are coupled in this equation. So it gets rather nasty. But anyway, we proceeded with this type of a technique, and eventually we were having troubles actually with the temperature equation. It was going unstable. Talked to other modelers, they said they knew about the problem, but there was no easy fix, or at least we didn't know what it was. And then one day Glenn came in and said, well, the hell with it. Let's include ion inertia in this equation. And then we can just step these forward both in time, substituting in here, et cetera. And that greatly simplified the coding by a lot. And we developed a semi-implicit differencing scheme for these equations. The advantage, it was simple. We could do all the ions at once, just have a do loop with ions in them. It's flexible. We could add more ions. We did shuttle burn releases with it. It's better at high altitudes because inertia along the magnetic field allows the velocities to maintain some sensible magnitudes, where if you don't have this term, the velocities get very large. And as I said, we do multi-ion speeds. Also, the downside is the time step. It's literally a few seconds. So computationally, the scheme we have isn't nearly as efficient as the implicit scheme. But we decided, given the simplicity, stability, and the flexibility, we would just run with it, and computer time is pretty much free. As far as the perpendicular dynamics, we looked at a number of cases. The Lagrangian grid is pretty typical of what people use. You simply have, say, plasma on a flux tube, and the E cross B drifts up to this position here, and conserving particle number and everything, you can decide how to redistribute the plasma at this upper field line where it was transported to. On the other hand, if you move the stuff up here, you have to replace this stuff, and so there are some issues then with replenishment of the plasma at different altitudes when you have a Lagrangian scheme. And our first code did use this scheme, but then we soon abandoned it, and we started to look at an orthogonal Eulerian grid. So it's a fixed grid, and so by orthogonal, the outer line here is the field line, so that's parallel flow, and then the perpendicular line is the direction of E cross B flow. And so you just transport the plasma. But the grid, again, is problematic. This goes up to 2,000 kilometers, so it's okay for that. If you tried to go to 20,000 kilometers, the grid becomes unwieldy if you want closed field lines. So I complained to John Lyon, my friend, at a meeting many years ago, and he said, well, the solution's easy. You take this bottom field line, you put 100 points, you put 100 points along here and just connect the dots. And there you have it, there's your grid. Okay, and then I said, well, it's not orthogonal. That means that the plasma, doesn't flow along this direction. It cuts across the cells. And his simple answer was deal with it. So this was after AGU. For Christmas vacation, the family went to visit my parents, and I spent about a week at my parents' house with a laptop dealing with it. So we use a finite volume method to solve these equations. The basic idea is you take a continuity equation, you can integrate over space to get the total number of, say, particles in a cell, and using Gauss's law, you can update it by calculating fluxes at the boundaries. So in this particular cell, if you want to know what the change is, you calculate the flux from this cell into here and subtract off the flux that leaves the cell. And that's how you update the cells. All right, so this picture doesn't do it justice. The point, though, is this velocity can be any direction. So if it's in this direction, you just dot it into the normal, and that gives you the flux. So it doesn't matter what the grid looks like. You just have to know what the geometry is. So when you set up your grid, you make all the calculations of normals, cell volumes, and things like that. And then it's relatively simple to do the transport for an arbitrary grid. And this is sort of an example of the three different grids. This is Lagrangian, orthogonal, and non-orthogonal. We did fill this region in. I just left it off at the time to show the problem that occurs when you lift up plasma without doing something to refill it here. But by and large, all the results are the same for the three different grids. So we went with the non-orthogonal grid. So then in the late 90s, when we had this thing running, we had a high school student. She came to work for the summer, and she was doing graphics for me. And one day, I went in to check on what she was doing, and she had a picture similar to this on the screen. And what I was looking for was the Appleton anomaly to make sure that was working okay or was being put into the model. But there was a big blue spot up here at about 1,500 kilometers. And this was like brand new. I'd never seen this before in any other model. I hadn't seen it in the data. And it's an unusual region of space at 2,000 or so kilometers. It's not populated by satellites very much and out of radar range. So eventually convinced ourselves this was real, and we wrote a paper on it in '99. And the idea was simply that when you had trans-hemispheric flows, plasma flowing this way, at this region there was a coupling of the O plus and the hydrogen, and when the O plus came over at nighttime and crashed down, it dragged hydrogen with it, and it left this depression in the electron density, and the depression's about a factor of 2. So it's not a giant depression, but it's there. Okay, so then I thought, well, the SUPIM code should be able to reproduce this. So I had met one of Graham Bailey's students, Brian McPherson, and I urged him to do a run with SUPIM for similar parameters, and he eventually did, and he sent me the results, and sure enough, the SUPIM model also had this high altitude depression in the electron density. So either we're both right or we're both wrong, but we were consistent with one another. Still, it would be nice if there was some kind of observations that would support something like this. And I spoke to Joe Grabowski at Goddard, and he said, well, you should go see people like Larry Brace, because they have a lot of instrumentation. And they had an instrument on the ISIS-1 satellite, which certainly at the time I thought was a cool name for a satellite, but maybe not anymore. It was an elliptical orbit from about 500 kilometers to 3,500 kilometers. And they gave me a Goddard report filled with pictures like this. This was their data set. So going through this, it's hard to see, but the point was it was here at nighttime at about 1,500 kilometers, and this is the density, and it goes down, and then it comes up, and then it goes down and back up. And so right in this region, there appears to be a little bit of a depression in the density in the measurements. And this is on a log scale, and this depression's on the order of a factor or 2. So this is the closest I've come to finding experimental evidence of this topside hole. This data, I've been told, has now been digitized, so I guess someone could go in and go through all the data sets to clean this up and look for this particular hole. The other thing, Hickomarker is going to be running at higher altitudes in the future, up to 3,000, 4,000 kilometers. And so Dave Heisel tells me that they may be able to detect this type of an effect. But this is something that was brand new to us. We found in '99. So in a sense, mission was accomplished. We wanted to build a 2D model of the ionosphere, and we kind of did, but why stop? So we went on to 3D over the next 3 years. And we moved on to the problem of equatorial spread F, which was I think Sid Osakow's favorite topic ever. And so part of that got imbued into me. And so this is from Booker and Wells, 1938 measurements in Huancayo, Peru. They were sending up a radio wave from about megahertz to 10 or 12 megahertz and measuring the return signal to map out the bottom side of the ionosphere where you reflected. And they noticed at night at times, this signal, rather than being relatively crisp, it broadened out and spread. So we're at the equator, we're in the F region, and the signal spread, so equatorial spread F. I actually don't know who coined the term, but this is visually where it could have come from. But now we have other observations, and these are, I guess, my favorite. John Nicolet's done a lot of work optically to detect these large-scale bubbles that develop in the equatorial region at night. And you can see here these dark patches. These are the depleted areas of the electron density that bubble up from below and rise up, and they structure. And associated with this, on this figure, there's a symbol, and that's a GPS satellite, and the signal's passing through this disturbed region. And what John shows is there's a lot of signal-to-noise ratio there, and you actually lose the signal. So this is sort of a clear space weather impact of equatorial spread F and the turbulence in the ionosphere on a system, specifically navigation systems, although it impacts communications also. So we took our 3D model to model this effect, but the bubbles occur on scale sizes of tens of kilometers. We would need below 10-kilometer resolution to really capture any kind of dynamics. And it was a bit much to try to put that type of resolution on the entire globe. So we kind of cheated, and we just took a small area shown here. This is a picture from a Besse paper. They developed a model, and that's their computational space, which seems to be an orthogonal grid. This is more like ours, non-orthogonal. Anyway, so we take maybe a 4-degree width here, 90 to 2,400 kilometers, plus or minus 30 degrees, and we can initialize the plasma and see if we can capture these bubbles rising. And this is one of our first results. So this is a contour plot vertically, horizontally. This is the F peak. This is the Appleton anomaly out here, and these light blue contours are electron density at 10 to the 4, and these bubbles rise up to an altitude here, it's about 1,000 kilometers, and then this low density plasma extends out along the flux tube, and there's even, you can see perturbations in the density at much lower altitudes, about 250 to 300 kilometers, and it's actually the perturbations and disturbances here that John Nicolet is observing, and then he just maps them up to this plane here. So you get this flux tube just moving up, and it's in 3D. So subsequent to this, a bunch of other groups have done similar type of work. John Rederer, Dave Heisel, Yokoyama's done some super high resolution things with this type of a model recently. And we were pretty happy with it, but then if you actually try to compare what a model looked like to real data, on the right is longitude, and this is altitude, and this is a large bubble forming. And then if you look at, again, the Kelly and Nicolet type optical images, these are very structured, bifurcated, and doesn't quite look like this. This looks like the work that was done at NRL in 1980. So what was the problem? The problem's numerical diffusion. So back in the 70s, there was a lot of work done at NRL on transport, and one scheme was developed called the partial donor cell method by Klaus Hain, numericist there. I'll try to give a flavor for how this works. We want to calculate a flux. Stuff is moving from left to right. We want to move some plasma from here to here. So we need to know what is the density that we're going to move. And this is the cell average density. And this is what we've been using. And this is the donor cell method. You just take the density in this cell and move some of it to this cell. But if you have a inhomogeneous plasma, you can see, well, if I do an interpolation here, take into account all these other values, I might want to use this value. This is a better looking value. It's closer to what reality probably would be at this position in space. Okay, so I'm going to use this. But what the partial donor cell method does, it basically says, okay, I'm moving some plasma from here into here, and I'm taking plasma from here into here. What if I'm not taking enough plasma out? I can get an overshoot here, and we don't want that. So we're going to correct the flux at this location and take more out so we don't get an overshoot. So that's what flux corrected transport means. In general, you would like to use this high order interpolated value, but sometimes they can give you numerical overshoots. So when we employed this method into our code, the diffusion goes away by a lot, and lo and behold, you have this glorious structure very similar now to what is observed spatially and optically. So that's pretty good, but we still haven't solved the problem we were going for. And that would be to try to capture this in a global code, because the whole global dynamics and electrodynamics define whether or not you get spread F. And so you'd like to know that self-consistently rather than just arbitrarily putting it into the code. And so one of the key features is this pre-reversal enhancement. So this is a plot of the vertical plasma velocity over Hickam marker as a function of local time. So in the daytime, the plasma rises, at nighttime it falls, so the ionosphere kind of breathes. And under certain conditions, you get this large uplift of plasma at nighttime, and this is usually associated with the generation of equatorial spread F. So I said it would be nice to capture this in a global model. and have spread F, but there's a gridding issue. So again, we kind of cheated. So Glenn and I, what we did was we put a high resolution portion of the grid into the code. So there were sort of two grids. There's a coarse grid that you can see the lines for, and solving the ionosphere globally on that grid gives the electrodynamics. Using the potential specified here and here, then we solve in this region to capture the small-scale effects. So in this region, there's about almost 1,000 grid points, and we have 7-kilometer grid spacing in this region. So the idea is just to run the code, generate the pre-reversal enhancement, and then self-consistently generate the structure. And so these are the results. The top curve is the density in the equatorial plane as a function of MLT versus altitude. So it's dawn, noon, sunset, and midnight. And so this upwelling here is associated with this pre-reversal enhancement, lifting up the ionosphere at sunset. Probably can't see it, but we put some perturbations in the plasma here. And as these perturbations convected into the night side, into darkness, we had these large-scale bubbles develop self-consistently out of the model. So this is the first time we were able to capture on a global scale equatorial plasma bubbles self-consistently. And then this is sort of a visualization of how big these things are relative to the Earth and what impact it would be. The contours are isocontours of the electron density. The red is roughly 10 to the 6th, and the yellow is 10 to the 4th. And this structure here is a density that was 10 to the 4th, but it started out below the F peak. So it's now risen through the F peak, and this is a bubble rising through into the top side. So this particular model doesn't have the high order schemes or anything in it, so you don't get a lot of structuring. Plus the gridding is still relatively coarse, but be that as it may, we were able to capture this effect globally. So now that we got off doing really good with this, the next best thing is to change to a different problem. So then we abandoned spread F and went to the plasmasphere. And these are isocontours of the plasmasphere. On the left is hydrogen, and on the right is helium. And these are for quiet times. And so the plasmasphere in the model has this toroidal donut-like shape, and it's pretty amorphous. We imposed a analytical convection field to simulate a storm, and doing that is shown down here, and now the plasmasphere is eroded and become quite a bit smaller, and on the dust side there's a sort of, can't quite call it a plume, but there's a bulge on the dust side similar to what's observed, although it doesn't show up quite as the stark plumes they observe in some of the satellite images in this particular run. Then we did some quantitative measurements. The dotted line or dots are data from Berube. These are electron density in the equatorial plane as a function of L shell. The blue curve is the best fit to this data set, and the yellow and the red are from SAMI-3 simulations of the plasmasphere averaged in longitude. So we capture quantitatively reasonable values within the model. So we've done quite a bit of work on the model, but I won't report on most of it, just the latest work that's being done right now by John Kroll. A few years ago at a GEM meeting, Joe Borowski reported these results from a geosynchronous satellite. During a period of high KP for almost 2 weeks of high KP, he saw these, he called them persistent plasmaspheric plumes, these large spikes in density in the cold plasma occurring regularly every day. And so the question is, you're depleting, refilling, depleting, refilling they tried to do some modeling, but it was hard to replicate this type of effect. But what John did was he developed a Wallenstern-Maynard-Chen potential that was KP driven. So he's trying to use information from the KP in an analytical model, then use that for the convection pattern in SAMI-3. And these are the results. This is the KP, the black is the data, and then the red is the SAMI-3 results overlaid on top. And it does a surprisingly good job at picking out the location and almost the magnitude for all of these peaks. And John will talk about this tomorrow and go through all the physics and what's going on in here. So I would recommend, if you're interested in this, that you listen to his talk. We're almost done with the paper. Apparently, as an aside, having Joe Borowski as a co-author is worse than getting a bad review. So we have to deal with him first. So the final topic of what we're doing now is there's a program at NRL to look at the E region, sporadic E, and metal ions. And that's being led by Doug Drob. And so metal ions are known to occur or be deposited by meteorites at perhaps 100 kilometers or thereabouts. But there are observations that they can get to higher altitudes. Ken Diamond on the HIRAS experiment at NRL saw them at 250 kilometers at mid-latitude. And very recently, Chu and Yu, with LIDAR measurements in Antarctica, saw heavy metal ions up at 200 kilometers and developed a theory and model to explain some of this. So the summer was partially spent by trying to incorporate metal ions into SAMI-3. And so the big issue is transport. There's a transition at roughly 150 kilometers where you go from unmagnetized to magnetized ions. So in the F region, where the ion collision frequency is much less than the ion cyclotron frequency, basically the plasma is just E cross B drifting. These are small terms. If you go very low in the atmosphere into the E region, where the collision frequency is very, very large, this term eventually will go away, and so the ions go wherever the neutrals take them. So there's this transition in the way the transport has to be handled, and no longer in the upper F region where there's a nice break between parallel and perpendicular. It gets all muddled up as you go through 150 kilometers into the E region. Anyway, as I indicated, with this finite volume method, it's relatively easy to calculate velocities and things like that and do the appropriate transport of calculation of fluxes. And these are some of the early results. On the left is latitude versus altitude. The simulation was initiated with a uniform layer of magnesium ions at about 105 kilometers and 10 kilometers thick. And then this is 24 hours later. And so the neutral winds have just moved this all over the place, but also there's been electrodynamics, and we're lifting some of the ions up to 200, 250 kilometers. And also in the southern region here, there's also ions up about 170. So this is, at first blush, relatively consistent with the observations of Ken Diamond and Chu and Yu. On the right, I tried to display how does these magnesium get distributed globally. So what I did is basically calculate a TEC of magnesium ions, simply integrate the ions, the number of ions vertically, and sum them up. Again, on the right, this started with a pretty much uniform bluish color. And then as 24 hours later, you get enormous structuring with latitudinal, longitudinal dependencies, high latitude patches of these ions. And it's all being redistributed by the primarily neutral wind and then interactions with the electric field. So this is something we're doing like literally right now. And this is the first set of results I can kind of show where I can say it's not complete garbage, because they were even more exciting. But so right now, things are looking reasonably good. We need to do a lot more testing on this, but I think we're pretty close. So before I digress into something else, this just kind of outlines what I said. Glenn and I were pretty proud. We got SAMI-2 running in about 18 months from pretty much nothing with new numerical techniques. And it was open source in 2000. A lot of people have picked it up and used it, so we're pretty happy about that. I didn't talk about other work we've been doing vis-a-vis coupling. There's been a lot of ongoing work and continuing work trying to couple to other models, namely the Rice convection model with Stan Zazakin. That has been funded by NASA. Coupling to TIE GCM at least one way. This is part of the ICON mission. And we have some recent NASA grants to couple SAMI-3 to GITM, Aaron Ridley's model, and also the WACM-X, the NCAR model. And these are also all ongoing right now. So I'll just sort of switch gears and talk about, I guess, something that came up last night, space weather. And I'll say some things that are kind of parochial, maybe obvious, maybe useful. But certainly there's a dichotomy between science and operations in terms of physics models. And so for physics models such as SAMI-3, we don't care about computational time so much. I mean, if to run a 24-hour run takes 72 hours, so be it. There's a lot of computational resources to throw at these problems with the high performance computer centers. So we're just trying to solve the problem. Certainly in operational code where you're trying to forecast into the future, doesn't have this luxury, and they have to be fast and lean. So I'll just, again, pick on only one topic in terms of space weather that I know a little bit about would be spread F. And I've tried to point out that this actually is a space weather concern because it does disrupt communications and navigations. But what do we really need to know to forecast something? Well, primarily, is it going to occur? Where is it going to occur? How long, et cetera? It's not clear we need to know the irregularity spectrum from 10 kilometers to 10 meters. So we don't need all the basic physics. We just have to know when it's going to occur, at least the lowest order for space weather. And are we there? And it's kind of like a yes, no / maybe. And I'm going to put this on Dave Heisel. Dave has a ESF model similar to ours, but one of the things Dave does is he ingests data at Hickamarka to initialize his code, and then he lets it run with this initialization of the data. The bottom line is, if his model says, hey, I'm seeing bubbles occur, bubbles occur. If his code says bubbles don't occur, for the most part, they don't occur. There's some rogue events he picks up. So this is kind of like, I would say, really good news that Dave has a model that has the right physics to discern whether or not we will have spread F occur. So rather than just run his model, it would behoove us, for him to just sort of identify the key underlying ingredients that drive the bubble that we just need to know the background without necessarily running the code. That's one thing. The other thing is, well, we want to predict spread F, but not tonight. We want to predict it tomorrow, the next day, et cetera, et cetera. So we need to know the thermosphere really well to know those conditions. So then we have to start relying on forecast models such as WACM-X or WAM, these whole Earth models, to try to do a good job on pushing forward for a forecast. And of course, we're going to need observations, and right now it's very exciting with ICON and GOLD coming online to provide a whole new set of observations where we lack a lot of information, particularly on neutral winds. So another thought, funding. We're trying to transition from science to operations in some sense, and I'm just focusing on models, not neural networks or any other thing here. Anyway, in general, DoD has I think a nice model for this type of thing, and I'm not sure how many people are aware of it, but they're called 6.1, 6.2, 6.3, and so on. And so 6.1 is basic research. It's NSF research, it's NASA research, answering fundamental science questions. 6.2 is then a transition from this basic result into something that's possibly operational. And then if you're successful, you can go to 6.3 where you start, really making something useful to the Navy or to DoD. In our case, it would be space weather forecasting. So one of the nice things about this feature of a way of describing research projects, I think, is one, the objectives are all different in every category, and two, there's separate pots of money for every category. And so in some of the things I've seen, at least in, say, LWS and stuff, there seems to be maybe a mixture of these things, and we're not sure what we're doing. But at agency night, there's a lot of work being done on space weather, and they're coming to grips with this, and I don't know the details of how they're going to do it or what's going on, but I think it would be, at least from the modeling point of view, behoove us to have some type of a structure like that where we really know what we're trying to do, why we're doing it, because this involves different talents, science vis-a-vis some software engineer. So I think that would help in terms of pushing us forward in this area. So I'll end by pointing out that this isn't unique to our area or to science in general. A few years ago, I was looking at the Slashdot website, which is sort of a techie website. There's a headline, there's a short paragraph about the headline, and then you can link to get more details about what the article is about. So it's about computer chips, codes, what have you. But this headline caught me. Sergey Brin and Larry Page are lousy programmers, Google engineer. So a few things. It's not ex-Google engineer. Two, it certainly gives us lousy programmers hope to maybe be rich and famous someday. And then you might think, well, did these guys just get lucky? I mean, they're just everyday guys, lousy programmers, and next thing you know, they build Google, they're rich and famous. What gives? So you read the article, and the Google engineer says, well, these guys are scientific programmers. So apparently, lousy and scientific are synonymous in the Google world. But be that as it may, what they said was, they came up with a really sophisticated search algorithm. They code the thing up the best they could, they run it, it works, and voila, the rest is sort of history. They demonstrated they could do it. But he goes on to ask, was the code efficient? No. Was it documented? No. Was it readable? No. Was it no? All right, so all the things you need for an operational code weren't in the original work by Page and Brin. And so it's sort of similar, I think, certainly to how I view coding, because my code is pretty scientific and is nowhere near ready for any kind of operational system. And it takes, as I said, a lot of different talents to bring that to fruition with all the different models out there. So I have a lot of time left, but I only have one view graph left. So I guess we have lots of questions. All right, so bottom line is I always like pictures, and I always like to visualize something. And so how can you visualize this scientific method versus an operational method? What would be a problem you could solve these two different ways? All right, so the problem is you need to replace a light bulb in a street lamp that's 30 feet high. And so here are two ways, and you can judge what's scientific and which isn't. So anyway, with that, thank you.
Thank you, Joe. Appreciate it. We have time for questions, of course. So Jim, if you wouldn't mind, there's a microphone up there at the front, so if people would ask questions in the microphone. This room is so big that the over 200 people in this room looked lost. So please, Jim.
All right, Joe, really appreciate your talk here. And you ended up talking about those different areas in the DoD in terms of the funding. One of the things that in the scientific area, really the issue, or one of the big issues really has been transitioning from a science code over to something that's operational. And the way I've seen it, and I wanted you to comment on that, because I think transitioning really is a totally separate activity. It's not research, it's not operations, but it's in of its own, it's incredibly important. And I'd just like for you to comment on that and how you see in the space weather enterprise how we can better address that transitioning aspect.
So my thoughts are along the lines of, you know, I agree, you know, it's this transition, and this is DOD's transition. The first start is they have different objectives. So in 6.2, there's no science. There's no science questions, there's no science issue. It's all been answered in 6.1, presumably. So when you want to transition, whether it be a magnetosphere model, ionosphere model, to something operational, we're not doing science anymore. Presumably, you've done it already and it works. And you, of course, you know, have to run tests to make sure you're still getting the right answer. But it's a different set of talents to, I would say, software engineer it, to streamline it. And it can involve different people. I personally am not the right person to write an operational code. So if you wanted to take my code, someone else would have to do it. So it's a different set of requirements in terms of the personnel that you would need. But I think, you know, I'm just repeating myself, but the bottom line is each category has a specific objective and has a specific pot of money. And they don't necessarily overlap other than, you know, jumping from one to the other. They're not mushed together in any way. So in going from 6.1 to 6.2, certainly you will have some of the same personnel here, but going from 6.3 and on, the basic research people are probably not there anymore. So I think you just have to clarify really at the outset what you want to accomplish and then define programs accordingly. So.
Take another question? It's not related to the question I had, but I'll just, couldn't hesitate to comment on Jim's question. To me, if you can demonstrate that the code is really ready or it's useful, would be useful for operations, I think putting it on a big enough computer and doing the extra coding is the easy part. The hard part is demonstrating that the code can really do what is needed. But that wasn't my question. My question is, when you had in the simulation you showed the global of the equatorial spread F, the global simulation with the high resolution wedge, and you had to seed the disturbance to get it to grow. Was the level of seeding that you put in a level that is pretty much always present naturally in the environment, or is it something at a level that would only happen under special, maybe rare conditions?
Well, one, I don't know. The level we put in at most was maybe a 15% perturbation. It might have been as low as 5%, which is somewhat significant. As far as how to categorize these things in terms of magnitude and ubiquity, one of the favorite things is looking at gravity waves. And that's part of one of our projects with, Wacom-X and Dave Fritz, is looking at gravity wave propagation and how much it does perturb the ionosphere. So I'll hopefully maybe be able to answer your question in a year or two. On the other hand, one thing we did do is run the code without seeding, and nothing happened, which is kind of like a good thing. That it shows the code wasn't just simply numerically unstable to drive this stuff. So the question of how big a seed you need, that's still somewhat undetermined. If I would put my Dave Heisel hat on, he would say the seeds don't really matter. And I think he thinks they're kind of ubiquitous. But that's, I believe, Dave's opinion.
Rod? I think you're going to have to move over to the microphone, please. I'm sorry there's only one.
Okay. I haven't used the semi-code yet, but I did use a few times of that NRL plasma formulary. I think it's very useful. Thank you. Just saying.
Thank you.
12,000 steps now. Joe, I want to say thanks for your presentation, first of all. It gave me the impression that everything's been done here. And so I'm going to ask you a question about things that haven't been done. I'd like to get your comments on just two things while I have the microphone. One is, in the plasmasphere, if you have a plasmasphere that's empty and refilling, is there a requirement for for the model to accommodate supersonic flow into the top side? And the second comment I'd like for you to talk to me about is how well do you think the electron heat balance, the energy balance in the top side ionosphere is handled? Are there rooms for improvement there in terms of photoelectron transport and heating of the separate species in the top side?
Okay, first question about supersonic flows. So we definitely get high-speed flows, tens of kilometers a second coming upward. But since it's a single fluid model or single fluid hydrogen, during the early stages, it kind of slams together, compresses, and goes back. It doesn't interpenetrate the way it does in real life. So there are some issues with the early stage refilling. But in terms of late stage, when things settle down, then the code runs pretty well. And John has done a lot of work on the refilling issue. The second problem on the electron energy stuff, we have a relatively simplistic model Graham Bailey developed, and we took out of SUPIM. But Roger Varney, at least with SAMI-2, did a lot of work putting a photoelectron heating and secondary ionization model into SAMI-2 based on a whole separate set of equation set that's first principles. So that's sort of in the toolbox. We've been thinking about taking it out, but Roger did all that work and did a lot of comparisons with some data and showed improvements with his model over the model we're using right now. I've spent most of my time actually worrying about densities and not temperatures and energies. So other than to say thanks to Roger for improving the model, that's where we are.
Rob, if you could make it really quick.
Well, okay, I will, but I'll try. So let me say that I think the modeling is great and the work you're doing is great, but it almost gives the impression that you have everything you need to solve the problem. And I think that there are some major things missing. One is, of course, the neutral wind. And in fact, Kudeki's not here, but he would argue if the wind and the drifts were going in opposite directions, that's enough to seed it. But also the electric field itself, I get the impression we assume it's the same versus altitude, sort of like in the auroral zone where it maps down the field line. But The electric field at the lower altitudes below the F peak, you know, there's shears, you know, the vortices and things. Are those in your models, and what do you say about that?
But we assume the potential is constant along the field lines. So, you know, you go to lower altitudes, the field lines converge or things like that, and beat changes, so you can change the electric field and drifts. As far as all these fine scale things in terms of turbulence and all that, in the post-sunset region, I think Hideki and Heisel showed there was, you know, a flow. So we've seen that in the global model. But in terms of even finer scale turbulence building off of that or something, we haven't gotten there yet, primarily because of resolution. But yeah.
All right, with that, we're going to close the session. And wait, just one moment. We're going to have an opportunity during the interchange between Joe's talk and Tomáš's talk. We're going to give the plaque and do the handshake ritual. But anybody else who would like to get their picture with Joe before he escapes, rush up and we'll get the picture because we have a couple of minutes before Tomáš's talk begins. So let's please thank Joe for a great talk.